Good afternoon. We're group three. My name is Christian Boyd.
My name is Suhyuk Choi.
And my name is Jariah Perez.
And for our final project, we decided to go with the flyball tachometer. And so here's a brief introduction. So the tachometer is a device used to measure rotational speed in revolutions per minute, or RPM. It has a wide variety of applications such as in engines, vehicles, and machinery to monitor rotating component speed. Tachometers are available in both analog and digital forms. Advanced models of tachometers are integrated in control systems for automated adjustments, and the flyball tachometer is one of the earliest type of tachometers and is a mechanical device that uses centrifugal force to measure rotational speed. Flyweights connected to a central shaft translate their movements into an RPM reading through a sliding collar or linkage. Flyball tachometers were commonly used in older machinery and steam engines through largely replaced by electronic tachometers. Flyball tachometers are valued for their mechanical simplicity and historical importance. And now here's some theory. So as mentioned before, the flyball tachometer is a mechanical device used to measure the shaft's RPM, and flyweights are attached to two or more arms which are connected to the shaft as shown. As the shaft rotates, the flyweights and the arms move outward due to centrifugal force. This causes the bottom sleeve to elevate upward as it is attached to the arms. As such, the RPM of the tachometer is directly correlated with the vertical portion of the bottom sleeve.
Design, implementation, experiment setup. The actuation module was used to construct a controllable rotating shaft while ensuring the stability for accurate measurements. The measurement module was used to measure the distance in relation to the revolutions per minute. The LCD display module was used in both mechanical and digital indicators to output the current RPM, and the LCD display was used as the digital indicator, while the marks along the shaft were used as mechanical indicators. Now diving in a little deeper to the design, the electromechanical design, the flyballs were attached to each arm to generate sufficient centrifugal force. A single spring was fit onto the shaft to allow greater RPM. The shaft was then mounted onto the DC motor, which was then clamped onto the vertical backboard of the rig. The electrical design, an ultrasonic sensor was placed 2 centimeters below the sleeve disc. An Arduino was connected to the ultrasonic sensor and was used to input the distance measured by the ultrasonic sensor. The LCD display was then connected to the Arduino to output the RPM reading. Moving on to the implementation. This project utilized a speed controller to regulate the voltage, which powered the DC motor. The motor typically required 1 minute to reach steady state due to the minor imperfections in the design, such as slightly higher center of mass and somewhat of loose fastenings between the plywood. Moving on to the demonstration, here in the short video of our tachometer rotating in various RPMs, keep in mind that although the construction of the rig was complete, the conversion of the distance to RPM wasn't calibrated just yet.
So for our evaluation and calibration, in order to ensure that the tachometer was accurate, it was put under various rotational speeds. Device readings were compared against a photo laser tachometer to determine the accuracy. The actual RPM measured by the store-bought tachometer was plotted against the distance displayed by the LCD. It was then linearly interpolated, from which we obtained the slope. This was repeated 3 more times to ensure consistent values. The mean value obtained from these tests were used as the numerical relationship between distance and RPM. Arduino code was then adjusted to display the RPM. The next slide shows our linear interpolation. As you notice, the distance of 2 centimeters and 0 RPM are not taken into consideration for our calculations. And this is because 2 centimeters was the closest we could set the ultrasonic sensor to the base disk for potentially risking contact. So for our calibration and linear interpolation results, average slope was determined to be 68 or y equals 68.33x. This meant that for every centimeter beyond the resting position of 2 centimeters, it was equivalent to 68.33 additional RPM. So for example, 1 centimeter above resting position will read as 206.48 RPM. This equation was implemented into the Arduino code so that the LCD display could show RPM instead of distance. Here is the Arduino code. And the photo to the right shows the line of code that multiplies the distance by 68 to convert it to RPM, as you can see on lcd.print distance times 68. So in conclusion, the design and implementation of the tachometer successfully demonstrates the ability to measure rotational speed with accuracy. Mechanical and digital parts, such as the LCD screen and physical markers, help display RPM readings. The evaluation process confirms the accuracy of the tachometer under various speeds, while calibration ensures consistency. Overall, through various components, we were able to display RPM as well as confirm the accuracy and reliability of our tachometer. Some possible improvements to be made are tighter tolerances, adjusted center of mass, safety/mechanism box, better quality equipment soldering, and better approximation methods. Now here's our BOM or bill of materials with the parts on display. And here's our bill of materials with their costs. As you can see, the total price is $166.19. However, approximately $66.19 of the total written costs were from parts owned prior to the project. So in reality, our total budget was about $100. And here are our references, and thank you.